Okay, so good morning, everyone. So today we have the part 2 of the lectures of Andrea Puhm on celestial holography.
Thanks, Alicia. So let me start by reminding everyone what we did yesterday. So I'm lecturing about a newly emergent program that tries to describe a holographic principle for quantum gravity in asymptotically flat space. And the underlying key point is that if you describe scattering amplitudes or the S matrix in 4 dimensions or in general d-dimensional bulk space-time dimensions, then it was found that you can recast the S matrix in a way that it looks like a correlation function on a sphere at the boundary of that asymptotically flat space-time, given by operator insertions on this celestial sphere. Can I maybe close the door? There's an echo. Okay, I don't want to hear myself twice. Okay, so the key underlying point is that we describe the S matrix usually in a momentum basis that makes translation symmetry manifest, but if we go to a new basis that makes Lorentz symmetry manifest, which acts on the sphere at the boundary of the spacetime as the global conformal group, then the S matrix looks like a correlation function on this sphere. The way that we found the map from this momentum basis or scattering amplitude to a boost basis scattering amplitude was via a so-called Mellin transform, which integrates from 0 to infinity over the energy and introduces a parameter delta, which we later found to correspond to the conformal dimension under the global conformal group. And what we did was we looked at the basis of plane waves, which make translation symmetry manifest. The IP.x, we parameterized massless momenta in terms of the energy omega and null vector q. And that object, when we Mellin transform it, turns into something that looks like 1 over q.x to some power. And this new object, this new wave function, we found to transform as a 2-dimensional or in general little d-dimensional conformal primary under global conformal transformations. Now, I've written this for a scalar here, but we also discussed that when you add the appropriate polarization vectors or tensors, then you can obtain conformal primary wave functions for particles with spin. These wave functions, let me remind you, depend on a bulk point or a bulk vector x, so this lives in R1,3, and also on a boundary point, and under simultaneous SL to Z Lorentz transformation, so SL1,3 is isomorphic to SL to C. If you do a Lorentz transformation on the bulk vector and a corresponding global conformal transformation or a Möbius transformation on the boundary point, Z bar, then this object indeed transforms as a 2-dimensional conformal primary. It also has to solve the 4-dimensional bulk equations of motions for the appropriate spin. So the massless Klein-Gordon for a scalar or linearized Einstein equations for a spin 2 wave function. And then we use these conformal primary wave functions to build boundary operators. And we did that by taking a suitable inner product, so the Klein-Gordon inner product, for example, for scalars, where we have a bulk operator and these conformal primary wave functions. And I reminded you that if in here you chose just the plane waves, then you would get creation and annihilation operators for particles with definite energy. If instead we put in here conformal primary wave functions, then what you get is an operator that creates a particle with definite conformal dimension delta or boost weight delta and spin j. And so in this way you can define a state by acting with these 2-dimensional celestial operators on a vacuum. Okay. So today what we're going to do is we're going to look at some limits of 4-dimensional bulk scattering amplitudes in a momentum basis and learn what it implies in the new boost basis. And the first limit was already, there was already a question yesterday. The first limit that we're going to discuss is collinear limits. So the first topic of today is we want to extract celestial OPE, so the operator product expansion, from collinear limit of momentum space scattering amplitudes. Now, these momentum space scattering amplitudes here, remind me again, we obtain in the new basis where they look like conformal correlation functions by Mellin transforming each of the external particles in this momentum space scattering amplitude. and in that way obtain something that looks like a correlation function of operators. And now we want to take limits of the object on the left-hand side in the momentum basis and extract on the right-hand side what it means to do to get the OPE. So we're going to focus on tree level, massless scattering amplitudes. And what is a well-known fact is that tree-level massless momentum space amplitudes factorize in the so-called collinear limit. So that means if we have two adjacent particles, I and j, the momentum pi, we can write in terms of some other momentum, capital P, and the adjacent momentum pj can then be written in terms of this capital momentum P in this way. So in this collinear limit, tree-level massless momentum space amplitudes factorize, and they do so by factorizing into a universal prefactor. Times a lower point amplitude. Namely now with this capital momentum P instead of the PIs and PJs. So let me write this momentum space amplitude on the left-hand side. Let me abbreviate it by A, curly A. So I have here, in general, an amplitude with particles of spin. So I have some helicities, Li and Lj. I make the dots range from 1 to n, so there's L1, etc., Li, Lj, ... Ln. And then I write here the dependence on the momenta. So they depend on momenta P1 to Bn with adjacent Pi and Pj momenta in between. And in the collinear limit, so Pi and Pj become collinear, as I've written out here. This factorizes in terms of this universal prefactor, which is called the split factor or split function, because we have now, there's one particle P that sort of splits into Pi and Pj. That's how we can think of it. And this will depend on the helicity of the particle with this momentum capital P. The original helicity is Li, Lj. And there's a sum over helicities of this combined particle. And this also depends on the momenta Pi, Pj. And then the lower point amplitude, which now only depends on a particle with helicity L instead of the I and J's. And the capital momentum P. Maybe let me write it here. So in this split function, we can have divergences, collinear divergences, and they come from the propagator between the particles I and j. So 1 over pi plus pj squared. And since I've, in this whole lectures focused on massless scattering, I will continue to do so. So here all the particles in my amplitude will be massless. In particular, these two particles will be massless. And so I can write this as 1 over pi dot pj. And the form of this collinear divergence is universal and can be extracted from the 3-point vertices. Okay? So much about collinear divergences in the momentum basis. Now we want to extract what it means to have collinear divergences in the new boost basis. Okay? So first of all, let me remind you that in the celestial parameterization of the momenta that we introduced yesterday, so that was, we took the momenta P mu to take the form omega j times, so I write this for each particle j. There was a 1 plus zz bar, j index now, z plus z bar, I times z bar minus z, and 1 minus z z bar. And that parameterization was one where we embed so there's a null vector that points towards the celestial sphere, and this one points to the point zj, z bar j. So in this parameterization, what we see is that the collinear divergences become a statement about the z's. So in particular, and this you can do as an exercise, you look at what, when you take the momenta collinear as I've written up there, what this means in this parameterization of the momenta in terms of the omega z and z bars. It means that we have the collinear limit in the celestial basis is given by zi equals to zj, or z bar equals z bar I equals to z bar j. What I've done here is, so far, we have worked in the usual signature, 1,3 signature. But what we want to gonna exploit now is we want to complexify the momenta, so we want to go to 2,2 signature, and then exploit what the collinear limit P, Pi collinear with Pj means in terms of these holomorphic and anti-holomorphic coordinates when we take a holomorphic or anti-holomorphic collinear limit. So this is a tool that people in scattering amplitudes use for computations. So we complexify the momenta. The z and the z bar coordinates are no longer related by complex conjugation, but they are treated independently. And then what we can do is we can independently take the limits zi to zj or z bar I to z bar j. And those will be a holomorphic or an anti-holomorphic collinear limit. So we take either the limits zi to zj with z bar I and z bar j fixed, or the other way around. Okay, so what we have done here is we have a momentum space scattering amplitude with a bunch of incoming and outgoing particles. Two of them are these particles I and j. And now we map this to a statement where the operator that is inserted at the point zi and the operator that is inserted at the point j become close, or for the anti-holomorphic limit. Okay? So as we take, and for now I will focus on the holomorphic collinear limit, which means I take zi to zj, and let me now abbreviate this with zij, so that is just supposed to denote the difference zi minus zj. So in taking that to 0, what happens now to these collinear divergences? So the 1 over pi dot pj will scale as 1 over zij. And similarly, if I take the z bar ij to 0, it will scale as 1 over z bar ij. So this will be the holomorphic collinear limit. Okay? So now we can make the following statement, that in our putative celestial CFT, when two operators that are associated to two gauge bosons are inserted near the same point, singularities Zi equals Zj correspond to singularities of the operator product expansion. Okay, is that point clear? So we started with some momentum space scattering amplitude. Our amplitudes friends told us that there is a universal factorization into a prefactor that's denoted here by a split, and the lower point amplitude. And collinear divergences that go like 1 over pi dot pj in the celestial parametrization become divergences in Zij. And when we translate this statement from momentum basis to the conformal basis, where our S matrix turns into these correlation functions of operators inserted at points, this collinear limit in a momentum basis turns into a limit where two operators become close. So performing looking at the collinear limit of momentum space amplitudes, upon the Mellin transform, they turn into the statement of taking the operator product expansion. Okay? So now what we want to do is we want to explicitly see what the operator product of two celestial operators gives us. What is the coefficient of this divergence, one of Zi minus Zj in the celestial basis. Okay, so to do that, to extract the OPE, the celestial OPE, we compute the Mellin transform of the momentum space amplitude in the collinear limit. So remember the Mellin transform, we have to do one on each of the external particles. So if I have an endpoint amplitude, as I have sort of indicated, or at least said in words over there, I have a product from 1 to n over these integrals from 0 to infinity, the omega over omega to the delta of the momentum space amplitude, and let me denote L1 to Ln, and in there are the Li's and Lj's, P1 to Pn. And then I have to take the collinear limit, Pi collinear with Pj. And that will turn into the statement that I have to take Zi to Zj, or Zij to 0, of my Mellin transformed amplitude, namely the celestial amplitude, which now, instead of the helicities, we said yesterday that we map the helicities to the spins under the global conformal group. So let me denote this by J1 to Jn. And then these amplitudes, after Mellin transforming, they no longer depend on the energy, they depend on the conformal dimensions delta. And let me just write this here again. So P goes like omega Q. Omega Q depends on Z and Z bar. So these depend on the conformal dimensions delta and the Z's and Z bars of each of these particles. Can you see if I leave this down here? Okay. Are there any questions on this point? Yeah.
Is it important that these are gauge bosons? I don't see where that has been
So
used.
in all of, so I want to compute OPEs of gravitons and gluons. You could also imagine computing the OPEs of scalars or other particles, but I'm just focusing on gauge bosons here.
Okay, thanks.
Okay, so let's do this. Let's explicitly see what this gives us. So in order to perform these integrals and then take the collinear limit, it is convenient if you do a coordinate transformation. Instead of integrating over these omegas, we want to integrate over the energy of the new momentum p that we get by replacing the pi's and pj's by. So we do a coordinate transformation. So I take the omega i's to be given by alpha, the same alpha as we had well, on the blackboard that I just erased. Omega p, and then omega j is 1 minus alpha omega p. So their sum is just omega p. And now I only want to extract the OPE of two operators, the ith and jth operator. So I will not worry about all these other Mellin transforms. I will just focus on the ones in omega I and omega j. Then I do this coordinate transformation, and now I want to just extract what doing this integral gives me. So from this whole line here, I will have terms that are given in terms of the integral in omega p. So the omega I is replaced by an omega p, and the omega j is replaced by an omega p. So let me just count. I have delta I plus delta j minus 2 from the omega downstairs. But in this coordinate transformation, I will get an extra power of omega p, and that will turn this 2 into a 1. And then, depending on what the split factor is, that tells me how this momentum space amplitude factorizes. So the split factor will depend on the energies omega I and omega j. I will get extra powers here. And then I will have the whole rest of the amplitude. And now let me look at what powers in the integral for alpha I get. So there's another integral in alpha. But alpha just runs from 0 to 1. And now let's count powers of alpha. So here I have an alpha, so omega I gets taken to the power delta I minus 1. Then there is the integral 1 minus alpha, which gets taken to the power delta j minus 1. And then in general, from the split factor, I will get also powers of alpha and 1 minus alpha because of the omega i's. So in general, what we will have, let me just write this with some variable x and y, which depend on the split factor. So this is all that we get. And the only dependence on alpha comes from what the split factor is. So whatever else in the remaining amplitude is, there's nothing contributes to this integral in alpha. So that's all there is. The power in x and the power in y, they depend entirely upon the split factor. And now some of you might recognize what this integral is. Any guess? No? Did I hear something? Yeah. That's the Euler beta function. So a product of gamma functions of these arguments, which depends on the conformal dimensions that you can extract from the split factors. So this is pretty universal. Again, nothing in the rest of the amplitude contributes to this integral, so all we need to know is the split factor, and then we know what this amplitude is, this piece of the amplitude is. Okay? So we already know that our operator product expansion will now be given in terms of this Euler beta function. Okay? Let me continue here. So now let's do an example. Let's take an example, amplitude of gluons. And I will focus on positive helicity, so I'll take all the L's to be positive, well, plus 1, let's say. All the LKs. And I will take them to be outgoing. The split factor will change whether the two adjacent gluons are outgoing, both outgoing, ingoing, or mixture, and also on the helicity. So I'll focus on this case, where my amplitudes friends tell me that the collinear limit of an amplitude with two adjacent gluons that are taken collinear has the following split factor. In the celestial parameterization, this is given by 1 over Zij. Then there is some power of the combined energy omega p, some factors of the individual particle energies omega I and omega j. And now let's extract from this what our operator product expansion would be. So we want to see what two gluon operators with dimensions delta I and helicity +1 inserted at points Zi and Zj. And then there's also some color factor A in principle, color factor B, conformal dimension delta J, again, positive helicity, so +1, inserted at point Zj. And I want to take them collinear. So I want to take Zij to 0, so the holomorphic collinear limit is what I want to take. And from the split factor, we already see that it has to scale like 1 over Zij. Then, because here I'm talking about gluons, and there's color indices AB, there's also structure constant, FABC, and the minus I for some normalization purposes. And then we already know that there should be an Euler beta function from this integral. And now we have to figure out what the arguments x and y here are. Okay? So to do this, let's focus on what the powers of the omegas and the split factors give us. Okay, so we have from the amplitude that I've written here, we have powers of omega p that are given by delta I plus delta j minus 1. That's just from the Mellin integral and changing basis. And then here, let's count. So there's an omega p here. So there's a +1 in power. But then omega I and omega j after the coordinate transformations also give powers of omega p, but negative, so -2. And so from this, we'll extract that the powers of omega p are delta I plus delta j -1. And next, the powers of alpha. So alpha has the powers of delta I -1 from the Mellin transform. And then there's a factor from the omega I here, so -1. And then 1 minus alpha has powers delta j -1. And there's also just one power of omega j, so also -1. And so from this, we can extract that the argument in the Euler beta function x is given by delta I -1. And because I had in the definition here x -1 is the power of alpha, so you read off delta -1 is x. And also y is delta j -1. Okay, so now we can put that into the Euler beta function. So this will depend on delta I -1. And delta j -1. And this operator, and then there's an operator in the OPE with some color factor C, which is inserted at the point Zj, Z bar j. And now we also have to read off what the conformal dimension of this operator is. And that we do by looking at the powers of omega p, because we have to, this is the new operator will come from a Mellin transform of an operator with energy omega p. So here I have to read off whatever the power of omega p is something -1, and this something is delta I plus delta j. So that guy. Just a second.
Should that not be a -2?
Oh, sorry, wait, this is a -1. Yeah.
Which, but from the line above, it looks like it should be -2. No?
From the line above, it should be -2. So there are some powers of omega that come in here. Did I write this right? I think it should be right. I'm sorry. So this is -2. Yeah. Sorry.
Okay.
Yeah. I was looking at the Graviton example, which is shifted by 1. So this is delta I plus delta j. Let me write it in this way. -1, -1, and then you read that off, and that is given by delta I plus delta j -1. Great, you're paying attention and following the calculation. Good, okay, so that is the OPE of two gluons in the celestial basis. And that's very nice, because we have now, so if we want to say that asymptotic flat space has a dual two-dimensional, in 4 dimensions, a dual two-dimensional conformal field theory, one thing that we should have in this two-dimensional conformal field theory is an operator product expansion. And we understood now that taking the collinear limit of momentum space amplitude under the Mellin transform, which switches to the celestial basis, gives us exactly that. And moreover, by looking at universal properties of amplitudes and that you can read off from 3-point vertices, we can infer what the coefficient in this operator product expansion is. Yes?
Yeah. Divergences when subsums of momenta add up to 0.
What are subsums of momenta?
Like the sum of 3 momenta, P1, P7, P11, equal to 0.
Okay.
Yeah, that would correspond to a sort of unusual singularity in the CFT, wouldn't it?
Maybe. I mean, there's lots of structures in amplitudes and singularities. We'll talk about another limit where you find other types of singularities later on. But
in CFT correlators, you only have singularities when points get close, not when some points move, when 3 points are in a particular position that is not sort of correct.
Okay, you're asking there are some singularities in amplitudes that do not seem to have an obvious interpretation in terms of CFT, given the
That's
kind of...
my questions.
Yeah, I don't know what these would correspond to. Yeah. So this is, by the way, stuff that has been found 2 years ago, 2.5 years ago, so this is pretty new. And there's certainly a lot to be understood about, I think, maybe even much more basic questions than what Stefan was asking. We have no comprehensive understanding of what all possible structures and singularities in amplitude correspond to in celestial amplitudes yet. So it's lots of stuff for you to do. Okay, so in view of time, so I also wanted to do the Graviton OPE. Maybe I can just do it on top of the gluon calculation just to sketch it. So in gravity, what we have, okay, let's do gravity on top of this here.
Andrea, there is a question in the chat.
Yes, gluons. So here we can talk about Young-Mills theory. I don't have to talk about QCD, but we can also talk about QCD. Celestial non-CFD, I'm not sure what that is.
You can also mute yourself and just ask the question directly if you want.
Hi, actually, gluons are the gauge bosons of QCD, which is a non-conformal theory. So I was thinking that this is related to non-conformal theory.
So there has been some work on trying to understand aspects of QCD in terms of this celestial CFT, notable when you look at soft limits in QCD. But apart from that, we don't really know what the holographic dual of QCD would be. So, but here we don't have to talk about QCD. If we want to talk about the OP of 2 gluons, we can talk about Young-Mills theory. And yesterday I said in words that Young-Mills amplitudes have very nice properties in terms of this new celestial basis. They give rise to well-defined celestial amplitudes. They give rise to this, they have this OPE when you take the collinear limit in Young-Mills amplitudes. So here, for example, I can think of an MHV amplitude in Young-Mills theory, and then taking 2 gluons collinear gives me this OPE. Yeah. I don't know the answer to all possible, in particular, real-world theories, what the holographic dual is. We don't even... So here, I said, I made a point in saying that it's an attempt at holography, and yesterday I put down the statement that celestial holography makes the proposal that quantum gravity in asymptotically flat spacetime in 4 dimensions can be described by a celestial CFT, which I put under quotation marks. So we don't really know what the CFT is. We know that there's a conformal structure, but we don't yet know if it's really a CFT. So not knowing even that, I cannot answer the question about what QCD would be dual to. Maybe that's something for you to look at.
Yeah. Thanks.
Okay. Okay, let's do just gravity real quick. So helicity 2, I will still focus on outgoing. And then there's a bunch of shifts happening. So, well, the first important point is that in gravity, we also have a z bar ij sitting upstairs. And so one point is, maybe somebody will say, oh, there are no collinear divergences in gravity. And indeed, if you take zij and z bar ij to 0 at the same time, there would be no collinear divergence. But I would like to take sort of an asymmetric limit where I keep the z bars fixed and take the zij's to 0. So then I have a collinear factorization. Now we have a factor of 2 in the power of omega, which will shift certain things. So for example, what we will get here is now this -1 that I didn't write before will indeed get erased. And what else will change? Well, this will stay the same. So what will change is that there is now a different dimension of this operator, and I have to erase all the color indices here. Okay. And I have to put the z bar ij upstairs, and then there's also a normalization factor kappa over 2. Okay, and this is now, and this is of course a spin 2 particle, and these guys are also spin 2. And this is now the OPE of 2 collinear gravitons. All right. And here I've just focused on tree-level collinear divergences, and I've just looked at the leading singularity, and we know that in CFT we have plus dot dot dot. And also I've just focused on the leading operator in the expansion, but we also have descendants here, and we can also include them. All right. So if you have questions on these OPE derivations, ask them now, because otherwise we'll switch gears and talk about symmetries.
So 2 questions. Mm-hmm. One is you had to take this funny limit for the graviton. Is that, like for gravity, do we not have collinear divergences for real momenta? Mm-hmm. Okay, so is there like a physical significance then to
this
limit? Yeah.
Yeah, so it seems that going to 2,2 signature, I mean, from the bulk point of view, that's not something that you would necessarily like to do, but in the Amplitude community has proven very useful. It looks like that there's a lot of nice results that you get that look like results in a CFT. And so maybe in order to, so you can ask, okay, what is the holographic dual? Is there a holographic dual? What is it described by? Yesterday, for example, we talked about defining these operators via the Klein-Gordon inner product for scalars. And then that brings us to some statements in distributive dual celestial CFT, which are unfamiliar from the point of view of normal CFTs that are used to. However, if you take other inner products, which from a bulk point of view don't necessarily have a bulk motivation, but they would have a CFT motivation, they will land you on things that are more familiar in CFT. Somewhat similar here, if you stick to 1,3 signature, you might not get all the things in the CFT that you would like, I mean, because it's also a Euclidean CFT, but if you switch to 2,2 signature, you may be able to describe things in a more CFT language and then use the power of CFT. Of course, at the end of the day, you want to, when you find some new results in this, so it's maybe a tool that you can use in order to understand something, to make progress, to use all the tools in CFT that we have. At the end of the day, you would want to, if you find some new result that you would like to make a prediction for the 4-dimensional bulk, then you would have to translate this back.
So I guess my concern, or what I'm not seeing well, is it seems to me like when we want holography or something, we want the holographic dual to teach us something about the bulk. But in this case, it seems like we need to know the bulk amplitudes to find out something about the dual. I'm wondering how that feeds back into the bulk.
Thank you for the question. So here, in view of time, because I have 2 lectures and I'm already running short in time, I focused on this route because it's the easier route. But you can also obtain these OPEs purely from symmetry considerations without referring to bulk amplitudes. You need to know something about the theory that you want to describe this OPE in, but you don't need the explicit split factors and the amplitude and so on. But I didn't describe this route because it would take already a full lecture to just describe that route. But just putting in, and I haven't talked about the symmetries yet that I need to derive this OPE. So you will use, Lorentz symmetry is already manifest in the spaces, so check. Then you use translation symmetry if you want to derive the graviton OPE. But you will also need to impose the symmetries that I'm going to discuss next, which is Bms symmetries or soft symmetries that come from the infrared sector of gravity. If you use all these symmetries, then you can derive that the OPE coefficient should be given by an Euler beta function, and you can derive what the argument should be. So this is a completely independent derivation that doesn't refer to bulk amplitudes. But I didn't do this because first I have to talk about the symmetries, and it's more complicated to do.
So just to make sure I understood, using just symmetries and the celestial CFT, we can derive graviton amplitudes.
Yeah. So
Okay,
you make an
nice.
ansatz for the OPE, which you will make an educated ansatz that you know something about gravity theory, but you don't need to know the graviton amplitude or what the split factors are. Okay, so now let's talk about symmetries.
So, can I ask a quick question?
Yes?
Can you compute stress tensor OPEs in a similar way in the CFT?
Yeah.
Okay.
But first I have to talk about the symmetries to tell you what the stress tensor is, and then we can write down the OPE. But spoiler alert, it will be the OPE that you expect. So the OPE of the stress tensor with another primary operator will be exactly that in a 2D CFT. The OPE of the stress tensor with itself will almost be that, it just misses the central charge term. Okay, so. Okay, so let me remind you again. So we said that Lorentz symmetry in the bulk is isomorphic to global conformal symmetry. More precisely, the proper orthochronous Lorentz group, SO plus 1,3, is isomorphic to SL2Z mod C2. So to be precise, here we have these transformations lambda, these 4x4 matrices with determinant 1 and lambda 0, 0, bigger or equal than 1. And over here, we have complex 2x2 matrices with determinant 1. So secretly, this is the condition that we had yesterday in the conformal transformations AC plus B over CC plus D, so this determinant condition is like AD minus BC equals 1. Okay? And now let me remind you, okay, in 4 dimensions, which I focus on, we have boosts and rotations. So I runs from 1 to 3. And then here, for the global conformal transformations, we have the dilatations, translations, spectral conformal transformations, and rotations. And this index AB runs from 1 to 2. And then we can also trade these generators by the usual global conformal generators, L0, L plus 1, L minus 1, and the same with the bars. Okay, so those are the 2D global conformal generators. Okay? And let's maybe do a quick exercise that reminds us why these conformal primary wave functions are boost eigenstates. So let's focus on the scalar one, which is given by 1 over q dot x to the delta. And let me pick this null vector q to be oriented so that it points along the x3 axis. So this is then given by, instead of having all the z's, so setting z to 0, then will just give me 1, 0, 0, 1. So this is my null vector, and then this guy just is proportional to x0 minus x3 to the delta. And now let's check that this indeed has conformal dimension delta and is a boost eigenstate. So for this, I need some embedding of these generators, L0, L plus minus 1, in relation to the 4-dimensional boosts and rotations. So in the embedding that you can find in the yellow book, the Di Francesco et al. Book, there's a relation between the boost generator in the 3 direction, and which is given by I x0 dx3 minus, plus x3 d by dx0. This is the dilatation operator, or written in terms of the L0s, this is given by I L0 plus L0 bar. And then rotation along the 3 axes is given by I x1 dx2 minus x2 dx1. This is the angular momentum in the 2D theory in the 1-2 plane, or L0 minus L0 bar. Okay? So this guy is that guy, and that guy is that. And now I can check what does L0 plus L0 bar on the wave function or on the operator that I can get from the wave function, what that gives me. And you can just check that when you act with x0 dx3 plus x3 dx0 on this guy, then indeed you get delta phi. And similarly for L0 minus L0 bar. Now this guy doesn't depend on x1 and x2, so this is just 0. And this guy should be the spin, so indeed for a scalar we have 0 spin. And then you can also check how L1 acts on phi and how L bar 1 acts on phi. So L1 and L bar 1 will be given in terms of the K1s and J1s, and K2s and J2s. This doesn't depend on it, so this is 0. And so in a sense, these phis are highest weight states. With respect to SO1, 3 or SL to Z. Okay? Okay, so now let's talk about symmetries. We have set up already the Lorentz generators, which are just the 2D global conformal generators. Okay, so first Lorentz. So we have the LMs and the L bar M's for m equals 0, 1, and minus 1. And how do they act? So now let me write everything in terms of the operators that we get from these wave functions. And now instead of writing them in terms of the conformal dimension delta and j, let me write them in terms of left and right weights h plus h bar and h minus h bar. So we can look at the commutator of these L's and these operators OH, H bar inserted at Z, Z bar. And there's a plus minus for whether the operator corresponds to an ingoing or an outgoing particle. And then if you compute this, what you will find is the following. Z to the m plus 1h plus z dz with this operator OH, H bar. And so, for example, for L0, what you will get is just H plus TC bar. So this is for global conformal transformations, and note also that Lm and Ln satisfy this algebra, which is the centerless Virasoro algebra. And now what we have to demand, because our amplitude should be Lorentz invariant, we have to demand that if you act with such a Lorentz transformation on the jth particle, and we do this for all the particles from 1 to n, then the corresponding celestial amplitude, which I denote by m here, curly m, is 0. And since we already know that Lorentz symmetry corresponds to global conformal symmetry, these are just the global conformal word identities. Okay? Now, a bit more unfamiliar is how translations act. And we had questions about that yesterday. Okay? So, for translations, the first thing to note is that we had the momentum, which was given in terms of an energy and this null vector q. In the celestial basis, I have to Mellin transform that guy. And essentially, what the momentum generator in this new basis will become is, again, this null vector but now we have an exponential in a differential operator, d by d delta. And from the different components of this vector, we can then construct translation generators. We'll have 4 of them. So we can take combinations of, let's say, P0 plus minus P3 and P1 plus minus IP2. And that will give me, so combinations like that will give us 4 generators, P, K, L, where K and L run from are given by plus or minus 1/2. So this is just to write down that we have these 4 generators, and then we can write down how they act on operators. So PKL acting on O plus minus HH bar will act in the following way. So they act differently on whether the particle is ingoing or outgoing. That is denoted by this plus or minus sign here. Then Z to the K plus 1/2, Z bar to the L plus 1/2. And then here comes the interesting piece. The operator gets its dimensions shifted. So H gets shifted by 1/2 and H bar gets shifted by 1/2, or in other words, delta gets shifted by 1. Okay? And so this is a kind of unusual property of celestial CFT. Then we can also write down what PKL and PK prime L prime are. Well, translations commute. And then we can also write down the PKLs and the LMs, just to have the full algebra there. Do this LM. K plus M and L. Okay, so that's the full algebra. And our translation symmetry of the amplitude, of the celestial amplitude, demands that when we act on the jth particle with these momentum generators, and let me just do this for one of those 4, where K and L is both minus 1/2, and I act on all n particles, so this has to be 0. And what this means, because when the Pj acts on the jth particle here, it will shift the conformal dimension. So this demanding translation symmetry of your amplitude means that we have a relation between amplitudes with shifted weights. Okay, so this is the way that the Poincaré group acts, and translations act in this funny way. And if anyone knows a CFT that incorporates the action of translations by having weights shifted, let me know. So somehow we seem to be getting a celestial CFT that has a few exotic properties compared to a garden variety CFT that you may encounter in ADS CFT. In some sense, they're more close to CFTs that are studied in condensed matter system or statistical physics systems, which are non-unitary. But they have this extra feature that translations act in this way. Okay, so now yesterday we talked about asymptotic symmetries, and we talked about BMS, super translations, and super rotations. Now, how do we get from the Poincaré group that I've written down here for generators that have M in 0 plus or minus 1, or KL in plus minus 1/2? Well, you obtain the BMS generators by extending the range of these generators to M in Z and K and L in Z plus 1/2. Okay, that was a very cheap way to introduce BMS from this point of view. But now let me also explain how BMS arises from these whole constructions of conformal primaries that we did yesterday. So yesterday we wrote down these conformal primary wave functions for scalars, spin 1, spin 2. Now let me state for you how BMS transformations arise from these conformal primary wave functions. So what we'll find is that we recover BMS transformations from conformal primary wave functions with special conformal dimensions delta. So it turns out that if you look at this, so yesterday we wrote down spin 1 conformal primary wave functions. Let me focus on positive spin, which were given by some polarization vector, mu. and a scalar conformal primary wave function, namely the one that I've written up there. But now if you take delta to 1, what you will find is that you can rewrite this spin 1 vector, this wave function, as a total derivative of some function, lambda, and we call it lambda gauge. And it turns out that this total derivative actually corresponds to large gauge transformations. So this is the gauge theory analog of BMS transformations, where this function here can be, in principle, be an arbitrary function of the angles. For spin 2 wave functions, if I take the dimension to 1, so this was given by mu times phi. Similarly, we'll find now a diffeomorphism. So, and this is the covariant derivative, d mu symmetrized x nu. Let me give this an index 1. And moreover, we can also show that this is given by the derivatives of a potential. Let me call it lambda gravity. And if you look at, so we have explicit wave functions here. So these are explicit function of the spacetime vector x and this boundary coordinate. And when you look at how this vector x nu looks like, you will find that it takes exactly the form that we had yesterday, where there is some function that's a function of the angles, du, when you look at its form at the null boundary. And so this conformal primary wave function with this specific conformal dimension delta, given by 1, corresponds to BMS supertranslations. So this you can just explicitly verify. You know the general form of a BMS supertranslation vector field xi nu. You take this conformal primary wave function, plug in delta equals 1, and you recover that you can write it exactly in the form of a BMS supertranslation vector field. There are more total derivatives or diffeomorphisms in the spin 2 sector. So when you take the conformal dimension to 0, you will also find a diffeomorphism. And this one, so this vector field that you write here turns out to correspond to BMS superrotations. So in this vector field here, you will find this, so this is a space-time vector field, asymptotic Killing vector field, and you will find this two-dimensional vector field on the sphere, y, that we had yesterday in relation to superrotations. Okay, any questions on this bit?
Yeah, I'm a little confused. I don't see how, so I recognize that this is how the gravitational field or a gauge field transform under these transformations. And I recognize that that may be written as the conformal primary wave function, also for the corresponding spins. Mm-hmm. But where are we taking these specific values of delta? And what's the meaning of?
Yeah, so the meaning is that in general, if you have some general delta, you just get this general form, some polarization vectors times phi delta. And this is just some spin j wave function. But if you tune this parameter, this conformal dimension delta, to the values 1 for gauge theory or 1 and 0 for gravity, then we will find that you can massage this into something that is a total derivative. So you know, so from this form, so if this is delta, this is not a total derivative. But when delta is 1 in this case or 0 in that case, you find that you can rewrite this as a total derivative. And then this total derivative, in the case of gravity, is a diffeomorphism. Then you can ask what kind of diffeomorphism is it. And then by comparing it to the way that BMS supertranslations and BMS superrotations look like, which I've written down yesterday, the vector field xi's that I've written down yesterday, you can compare them, and then you will see, oh, this guy, the dimension 1 conformal primary wave function, is precisely a BMS supertranslation. And the dimension 0 gravity wave function is precisely a BMS superrotation. So this is something that you find. So somewhere in our basis of conformal primary wave functions, we should, so yesterday we talked about wave functions where delta was on the principal series because those form a complete basis. So these wave functions form a complete basis. And then the question is, okay, and this corresponds to finite energy wave functions, but we should also recover our gauge fields and gauge transformations in the celestial basis. And what I'm saying is that the gauge fields are obtained by taking delta not in the principal series, but by going off it. Okay, delta equals 1 is still kind of on the principal series, but then delta equals 0 is off the principal series. And so my claim will be that, that the gauge fields and the diffeomorphism fields will lie in, well, let me say it in the integers, but actually I mean 1, 0, and then negative integers. So this is where we'll find gauge transformations. So these should be part of our CFD. We know that they're physical in our bulk spacetime. We have these asymptotic symmetries. They are there. In particular, these modes will include also global gauge transformations and translations, and this guy will include rotations. So the global transformations we know have to be there. We know that they can be enhanced to gauge transformations that do not fall off at the boundary and in particular depend arbitrarily on the angle. And so what we recover here is that in the conformal basis you find wave functions or corresponding operators which give rise to these asymptotic symmetries by picking the conformal dimension to lie off the principal series in the integers.
So is this accurate to say that, for example, the graviton can be encoded with celestial conformal primary wave functions with j equals 2, but any delta in the primary series?
Yeah.
Or the principal series?
And a graviton with some finite energy will lie in this delta.
Sure.
And then a graviton, which I will talk now about, a graviton with 0 or soft energy will lie in these deltas.
And those are the only ones that are affected by large gauge transformations?
No, those are the ones that generate large gauge transformations.
Right, that's the part that confuses. So like,
Okay.
I think I can ask probably after the,
Okay.
yeah. Thanks.
So the point is finite energy wave functions map to conformal primary wave functions on the principal series. And now what we are uncovering here is that wave functions with delta in the integers have something to do with symmetries. So conformally soft symmetries. So first I have to tell you what I mean by soft symmetries in the usual momentum basis. So yesterday I drew in the introduction or motivational part, I drew this infrared triangle where I said that asymptotic symmetries are related to soft theorems. So now let me sketch for you what I mean by soft theorem. So in a similar way as collinear limits are universal, give rise to universal factorization, soft limits give rise to universal factorization. Of the S matrix in a theory of massless particles. And these factorizations arise when you take the energy of a massless particle to 0, and this is called soft. So I have an amplitude, a bunch of ingoing and a bunch of outgoing particles. And then I take one of the particles, one of the external particles, and take its energy to 0. So here I can be talking about gauge theory or gravity. My momentum p mu is again given by omega times some null vector, and also by some polarization vector or polarization tensor if I'm talking about, let's say, photons or gluons and gravitons. So, sorry, epsilon mu nu, and they can have positive or negative helicity. So when you take the energy of this guy soft, what happens is that the amplitude factorizes into something that I will call a soft pole. So that's the leading term in an expansion near omega equals 0 times the lower point amplitude without that soft particle. Now the leading contribution in this soft limit comes from propagators where the kth hard particle in the amplitude, whose energy is finite, is dotted into this guy whose energy is taking soft. So this is again has a leading term, and I'm focusing on the case where all the particles are massless. This can be generalized to massive hard particles. So again, similar as before, we have as leading term one that is a pole in the energy. And so let me write this in terms of formula. So I have an n plus 1 particle scattering amplitude where the plus 1 guy has either positive or negative helicity. That's the photon, gluon, or graviton whose energy I'm going to take to 0. And then let me explain what this soft pole factor here is. So that's the leading term in an expansion. So that's this guy here, 1 over the energy. And let me denote there's some factor that depends on the momentum of the hard particles, the momentum of the soft particle, and also the polarization vectors or tensors, and the helicity of that particle. And then I have plus dot, dot, dot. So there are subleading contributions. And the first one is a contribution that is of order 1. And then in gravity, I can also write a further universal term that scales with the energy to the positive power. And this is then multiplying the endpoint amplitude where this soft particle is removed. And so what has this to do with symmetries? So I can write this amplitude as an insertion of this soft particle into the otherwise S-matrix element with just the hard particles. So then let me denote this soft insertion by the operator. So I want to annihilate this soft particle in the amplitude. So that's A, it can have plus or minus helicity, and it depends on this energy that I'm taking soft. So this amplitude corresponds to the soft insertion here. Soft. This is the soft mode. And this can in general be written as, well, a sum over these S's. Let me do this in generality, Si plus minus. And then I also have to sum over K in the in and out states, because I can have my soft particle either attached to an ingoing or to an outgoing. And I sum over all the i's. So that gives the 3 terms here, plus potentially further subleading terms. There's an omega to the I minus 1. So when I is 0, this is the pole. And the S-matrix element without that soft piece. And let me call this the soft factor. And how is this related to symmetry? So somehow this universal factorization property, it kind of smells like there should be a symmetry that explains the existence of such universality. So we asked that there is some conserved charge associated to this symmetry. Let me call it Q. And if this is a symmetry, then it should commute with the S-matrix. So if I want to wedge this charge between in and out states, so let me write this as follows. So there's some charge that should act on my out states, which I denote by Q plus S. And then there's some charge that should act on the in states. Let me denote this by a minus. The question is, so this I want to be 0. And the way why I wrote plus and minus here is because, remember, we are in asymptotically flat space, where in states are defined on square minus and the out states on square plus. And so I want to have a charge that's defined on square minus and a charge that's defined on square plus. And then what I will do is I will split the charge into two pieces that I will just give a name, QS and QH. And then I'll just rewrite this whole thing as Q plus S, Q minus S, and this should be given by minus. Same thing with the QH. And in order to explain really that what I'm writing here is supposed to incorporate that soft theorems are related to asymptotic symmetries, namely to BMS or large gauge transformations. So in order to show that would need a whole lecture or two. So instead of doing that, let me just tell you that there's one piece in the charge which is related to this soft mode insertion here. So that's why it's called QS for soft. And then there's another piece in the charge which is called QH or hard, which when you act with this charge on the hard particles in the amplitude would give you exactly this soft factor that arises on the right-hand side of the soft theorem. So I did not show this to you, but this is what you find after several pages of computations. And so the statement is, so here I've talked about gauge symmetry, large gauge symmetry that comes from some photon or gluon. If I take an amplitude that has a photon or gluon and I take its energy soft, then the corresponding soft theorem can be recast as this conservation law here, where so the leading soft photon theorem, by which I mean this 1 over energy pole, leading soft photon, corresponds to large gauge transformations, in particular to such a large gauge transformation. The leading soft graviton theorem, so now I take a graviton whose energy I take soft, that can be shown via following this series of steps and then doing some more work, that this corresponds to BMS super translations. And then there is a subleading soft graviton theorem which comes from the order omega to the 0, so order 1 term, and that corresponds to BMS super rotations. Okay, so I did not show you the steps here, but I just sketched it. It's a bit of a lengthy computation. But the point is that on the one hand side, we discussed asymptotic symmetries. From some asymptotic symmetry analysis, we found that there are asymptotic killing vector fields which give rise to BMS super translations and super rotations. You can do an analogous analysis for gauge theory and you find large gauge transformations. And these are related to universal aspects of quantum field theory scattering amplitudes, which arise when you take the energy of a photon or the energy of a graviton to 0. There's an expansion in the energy going to 0, and the terms in the expansion correspond to different kinds of asymptotic symmetries. Okay. So now, maybe the last thing that I want to explain to you is what this corresponds to in the celestial basis, what is soft theorems and the asymptotic symmetries that I just described for you as arising from specific weights for the conformal primary wave functions, how this shows up in the conformal basis. So we call them conformally soft theorems. In contrast to the energetically soft theorems. So naively you could say, okay, so these universal properties arise when you take the energy to the 0. But we learned that we go to the celestial basis, to like the celestial CFD, by integrating over the energies. So you can say, what does it even mean to have a soft particle? I integrated over all the energies. Well, it turns out that there is an analog, a celestial analog of the statement of taking the energy to the 0. And the analog statement is taking the conformal weights to special values. So heuristically, let me show you how this comes about. Instead of integrating to infinity, let me just look at the low energy sector. Anyway, I'm interested in the low energy behavior of amplitude, so let me put some cutoff here and look at what this integral, this Mellin integral, becomes. So this is what I have to do in order to transform from the momentum to the celestial basis. And now in this soft expansion, I have just powers of the energy, powers of omega. So let me denote this by a k here. Now if you do this integral, you find something that looks like this. So there's this cutoff energy. And then what you will find is that there's a pole. And here the k to map this to the soft expansion would start from -1, 0, 1, and in principle the expansion can go on. So these are the values of k. And so you see that the energetically soft limit, so the universality that you get here will be mapped to one where you look at the behavior of the celestial amplitude, which arises, so in the conformally soft limit, the celestial amplitude will have poles. And so the energetically soft universal properties of the momentum space amplitude will be mapped to universal properties of celestial amplitudes that are given by these poles. So poles at delta equals to 1, 0, -1, in Z. And this is what I promised you before. And this is not in 1 plus I R, the principal continuous series in general. Okay, so the expansion in soft factors gets mapped to a series of simple poles. And let me just state for you what the soft theorem for photons and gravitons becomes in this new basis. So the conformally soft photon what I will do here is I will take my celestial amplitude and I will take the conformal dimension of one of the photons in this amplitude to 1. This is what we found before, where we should look for large gauge transformations. And what I will find is, so when you take delta to 1 of some endpoint celestial amplitude that has a photon in it, let's say with positive helicity, delta I, Z J, sorry, Z I, Z bar I. So this is given by the soft factor, which in the celestial basis where we use the parameterization of the momenta in terms of these Zs, takes a very simple form, and it multiplies the amplitude with this extra photon removed. Okay, so this has a nice form, and when you stare at it long enough, and you remember that these celestial amplitudes are actually given by correlation functions of operators. So there's an operator O1 to On. And now what I'm saying is that in the limit, when you take delta to 1, this becomes the same. So the correlator without this extra particle, it has this factor Q over Z minus ZK, sum over K. And then on the left-hand side, so what this smells like, it smells like a two-dimensional water density for a current. So this extra particle in here, which has dimension 1, is a current. In terms of the weights h bar, so delta is 1, and in terms of the weights h bar, it is a 1,0 weight operator. And so we find that the soft photon theorem in the celestial basis is a two-dimensional water density with current J. And this current J, this is a 2D operator. You can construct it from this definition here, where the conformal primary wave function that you plug in is this conformal primary vector with dimension equals to 1. So we understand that large gauge transformations, which in the celestial basis you find by these conformal primary vectors with dimension 1, they give rise to two-dimensional conserved currents, and the water density for this current precisely corresponds to the soft photon theorem. Okay, then what about gravity? Conformally soft graviton. Again, I told you that when the dimension goes to 1, there is a pure gauge term, a pure diffeomorphism term in the conformal primary wave function. So let's see if we can find something interesting when we take one of the gravitons in the celestial amplitude to 1. So this is now spin 2. So what we'll find is precisely the soft graviton theorem, which, let me tell you, takes, in the celestial basis, takes this form. So there's now not a holomorphic piece, but there's some dependence on the z's and the z bars. And the remaining celestial amplitude without this graviton, whose conformal dimension I'll take to 1. But now if you remember, so BMS supertranslations include translations, and we have seen that translations act on operators by shifting the conformal dimension. So if I have in here a supertranslation operator, then in my lower point amplitude on the right-hand side, I will have conformal dimensions that get shifted. So we saw earlier that when you have an amplitude where you act with the momentum pj on the jth particle, then the jth conformal dimension will be shifted. Similarly here, the conformally soft graviton, when you take delta to 1, will correspond to BMS supertranslations. So in this limit, we'll have to shift the conformal dimension of the, in this case, kth particle. And now this doesn't look like anything that I know in CFT, but what we can do is we can take a derivative with respect to d z bar to get rid of this enumerator. And then what we'll find is some correlator, O1 to On, which now has a holomorphic right-hand side. The kth guy has its dimension shifted. And then on the left-hand side, what this conformally soft limit amounts to is I have the insertion of another current. Let me call it PZ. And this current, you may call it BMS supertranslation current. Okay, great. So we found another current in the CFT, and this current in the CFT has to do with BMS supertranslations, and it also gives rise to a two-dimensional water identity. For this current that is noted by P. Okay? And now let me just write down the water density, and I guess this is maybe what I'll end on. There's a water density also that arises when we look at the subleading soft graviton theorem. So there's a subleading conformally soft graviton. And this arises in the limit where the dimension is taken to 0. So that was our extra diffeomorphism for spin 2 conformal primary wave functions. And what the subleading, or the celestial version of the subleading soft graviton theorem amounts to is another water density, and this water density is 1 for a stress tensor. Okay, so now we have recovered a couple of things that we would like to be there in a CFT. We have, first of all, we talked about the operator product expansion, which we can infer from some holomorphic or anti-holomorphic collinear limits, or via symmetry considerations, and the symmetry considerations that would have to go into are the usual Poincaré symmetries or global gauge symmetries, but also these soft symmetries that I've stated here. plus extra soft symmetries that would arise if I kept going in this expansion in the energy to more and more subleading orders. So I do not have time to talk about this, but there's a whole semi-infinite tower that does not only include the leading soft photon and graviton, the subleading soft photon and graviton, the subleading graviton, maybe photon, but more and more terms in the soft expansions, and using what these extra terms in the soft expansions become in the celestial basis, I can put some constraints on amplitudes, and in this way we can also recover the celestial OPE just from symmetry considerations. Okay, so let me see here. Then we have found that there are conserved currents in the celestial CFD that we obtain by looking at conformal primary wave functions with specific conformal dimensions. And among them here, the last thing that I wrote is a stress tensor for this 2D CFD. And this is also something that we would like to have. And one thing that I would like to point out is that, so this water identity is the usual one for a stress tensor. But the fact that here there's a number, the weight of the kth hard particle in this correlation function, so we have a number when we go to the celestial basis. But the corresponding statement in the momentum basis is not a number, it's an operator. And in particular, it's an operator that looks like omega d omega. And so you can already, from the subleading of graviton theorem, if you Mellin transform it, you can already, if you start with the subleadings of graviton theorem, you can already recover that there's some sort of water density structure. But in the momentum basis, this is an operator. And so this is another motivation for why we should do this Mellin transform in order to find actual two-dimensional water densities, which have bona fide water density expressions where this guy is diagonalized. So this was a motivation for doing this Mellin transform, getting rid of these energies and replacing this operator by some actual number, which is the conformal dimension or the conformal weight of a celestial operator. Okay, so I think we started a little late. Do I have, just to sketch one more universal piece of physics in this putative celestial CFD, and then I will end. Okay, so we don't really know yet what this celestial CFD is. It was already pointed out that a lot of what I showed you yesterday and today starts from some knowledge of amplitudes and tries to recover some nice CFD structures. And ultimately, we would like to start just from a two-dimensional intrinsic definition and then learn something new on the bulk. And there has been a lot of work on understanding the conformally soft sector of this celestial CFD. And it seems like that this part of this putative holographic dual might be bootstrappable. So there might be some powerful things that we can say just in this conformally soft sector. Another universal thing that we can do without actually knowing what the CFD is we can try to organize everything according to some principle or to some symmetry. And the first thing that comes to mind is you want to organize everything in terms of multiplets with respect to the global conformal symmetry. So we want to organize everything in terms of representations of SL2Z. So let me start by saying something elementary. So if we have a state with weights h and h bar in a 2D CFD, then this state is a primary if it is annihilated by L1 and L bar minus 1. Then from there, we can construct descendants. By acting with L minus 1 or L bar minus 1 a number of times. And I've given you before the way how L-1 act on some operators, and you can read off from there that L-1 and L-bar-1 just correspond to derivatives in the Z and Z bar coordinates in this 2D CFT. And now I can ask, well, I can construct all these descendants, but when does a descendant become a primary itself? So I can look at a descendant, H prime and H bar prime, which is given. Let me just focus on the holomorphic part of this theory. By acting with L-1s a bunch of times, I can ask, when is this a primary descendant? So that means the L1 and L-bar 1 have to annihilate it. And this is the case. So let me write this out. When L1 acting on this descendant that's constructed by powers of L-1 is 0. And there you find that the weights of the parent primary that you started with has to be of this form, 1 minus k over 2, where k is a positive integer. And then your primary descendant has weights 1 plus k over 2. Okay? And now you can look for all the primary descendants in your theory. And finding all these primary descendants will tell you where interesting operators lie. And in particular, these interesting operators will be related to symmetries. So let's say you start with some primary given by acting with this operator OH and H bar. Let's say this is a primary. And then you act with this operator, on this operator with L-1 to the k to get a descendant. And then if the primary operator at the top satisfies these conformal weights, then the descendant that you will find here is also a primary. So this is just given by acting with k z derivatives on this parent primary. Okay? Now you can do this whole thing also for the anti-holomorphic part. So then if this operator, in addition to satisfying this condition, also satisfies the same one with h and k replaced by bars, then you can find another primary descendant. And these operators may themselves descend to another descendant that's also primary. So in 2D celestial CFT, you can find such conformal multiplet structures, which we call, I'll give it the flashy name, a celestial diamond. So there's this diamond-shaped form of multiplets in celestial CFT. And the corners of this diamond-shaped multiplet structure tell you something about the conformally soft sector. So in particular, operators on the corners on the left and on the right. So these operators will have some dimension. Let me call it delta again. And these dimensions will tell you where you find soft theorems. So if you give me a celestial amplitude, and I look at the conformal multiplet structure of the operators that are in the celestial amplitude, then the left and right corners are precisely those deltas for which you find a soft theorem. So for example, for gauge theory, this is a symmetric diamond. This operator on the right here has dimension 1, and indeed for dimension 1 we found that there is a universal factorization theorem of correlators where the operator with dimension 1 is the conserved current. And then the bottom guy here, in normal CFT, this would be, so the structure of conformal multiplets will tell you that there is a conservation equation down here. And so the bottom guy will tell you something about charges in your theory. And in fact, if you plug in these operators that you construct from conformal primary wave functions, this bottom corner of this celestial diamond will tell you something about the soft part of the charge of the asymptotic symmetry that's related to these soft theorems. So let me just sketch this for you. So there's a charge that you get by integrating over the sphere. And then there's some symmetry parameter, which in the case of gauge theory is just some function. And in the case of gravity was the Bms supertranslation vector field or superrotation vector field. And let me give this a name. So there's some operator that I call O soft at the bottom of this multiplet, which tells you something about the charge, the BMS charge in the case of Bms symmetry. Okay, so I think I'm out of time. This was to tell you that if you use symmetry, you can organize your data in your CFT by looking at where all the primaries and primary descendants lie. You can easily read off where you find the celestial analog of soft theorems and where you find the charges of the asymptotic symmetries that are related to soft theorems. And then moreover, if you take all of the primaries that have primary descendants, then in the case of gravity, what you can do is you can look at the algebra of all these soft operators. So all these soft operators, what these are in 1, 0, -1, and all of them infinitely many. And then you can use the OPE that we derived this morning to compute commutators between two such operators. And what you will find is that there's an infinite dimensional symmetry algebra that contains all the soft gravitons in the celestial CFT. And this symmetry algebra goes under the name of W1 plus infinity and has led to a lot of activity since its discovery a year ago. So there's a lot of symmetry that arises when you look at the celestial basis for asymptotically flat spacetime. And the many open questions. One question is, how much symmetries do we have? So this celestial basis seems particularly well suited for asking about the symmetries of nature. And we found surprises that there are more symmetries that we initially expected. So in some sector of gravity, there's this infinite dimensional, very large symmetry algebra. And one question is what are all the symmetries? One other question that you can ask in this business is, well, we've talked about this asymptotically flat holography from using that Lorentz symmetry becomes global conformal symmetry, and then we get this codimension 2 holography. But can you actually derive flat space holography from ADS CFT by taking some flat space limits? That is one of the open questions. There's many more open questions. Also how you recover this other dimension, the time direction that we didn't talk about. And there's proposals for some Carolian perspectives on celestial holography, which would be a codimension 1 holography, and so on and so forth. So I think I'm out of time, so let me stop here, and if there are any questions. Yeah.
Thank you very much, Andrea. Do you have more questions?
So, two different questions. So first, in usual CFT, when you have a state that's both primary and descendant, usually it's like a signature, you're not constructing irreducible representations, there's null states. Does that concern arise here?
Thank you for that question. So indeed, naively, you will find that there are null states. And in particular, what you have in usual CFT, where we can do radial quantization, is that L dagger n. So in the usual 2D CFT, you find L dagger n is L minus n. But what we find from our 4-dimensional perspective, where we start with the rotations and boost generators, is that we get L dagger n is minus L bar n. So there are some relations between the generators that are not familiar from our usual CFT. If you had that relation, so that would arise when you have actual null states, so that have a 0 norm with all the other primaries. But what we find actually is that we don't get 0 norm, we get contact terms. And this is related to the fact that from the 4-dimensional bulk spacetime perspective, where we have unitary Lorentz generators, you get this relation between the global conformal generators. Now, there's one way to get around this, is if you want to really insist on having some dual CFT where you can do radial quantization, instead of taking the inner product to be the Klein-Gordon norm, as we talked about yesterday, you can input here another integral transform on the celestial sphere, which is called a shadow transform. And then you can effectively recover this standard relation that you know from CFT, and that you can talk about null states. And the reason, so here, the point was to be careful about all the contact terms that appear, but still finding that you don't get exactly 0 about contact terms still gives you a symmetry up to the insertions of these, up to the places where you have these contact terms, where you have non-zero support.
Okay, thanks.
So if you close your eyes and say, okay, I get null states here, then you still get your symmetry generators and everything.
And the second question is, so This has all been specific to 4D, BMS4. As far as I understand, there's BMS3 is an analog, and in 5 and higher dimensions there isn't one. Is there some like non-unitary quantum mechanics you can write on some circle, or is this story valid for BMS3?
Yeah, so there is work on BMS3, so here a lot of the stuff that we've been trying to understand is about correlation functions, where you have 4D scattering amplitudes. In 3D, you wouldn't have propagating gravitons, so we cannot talk about graviton correlators. We could still talk about gauge theory. I don't think there has been much work on this front, but it would certainly be interesting to look at that. In 3D, there's another thing which is that this Carolian aspect, where you have a codimension 1 holography, is also better understood there. So there are some things that are better understood, but there are also some things that are special to 3D, like not having propagating gravitons. So there are some things that we cannot address there. For example, this guy, wouldn't be there. In high dimensions, people also make proposals for BMS symmetries. It may be on a bit of a different footing, and that's related to the fact that or maybe related to the fact that in 4 dimensions we have infrared divergences, and we don't have them in high dimensions. So in 4 dimensions, BMS is necessary so you can explain, so normally when you have infrared divergences and you exponentiate them, normally you would get 0, and that's 0. So this is related to the fact that we have Bms symmetry. In high dimensions, we don't have infrared divergences, so there is a priori not such a need for having this extra infinitely enhanced symmetry. Yeah, I'm not sure if this makes sense. This is very short, crude answer to your question.
No, this
There's
is
of course much more to be said, and then we can maybe discuss.
Okay, great. Thanks.
More. Yeah.
Okay, maybe one last question. Yeah.
Just to be clear, without the Einstein-Hilbert action, you can recover gravity amplitudes from the celestial CFT perspective?
Well, if you...
Like with only input from the symmetries, I mean.
Well, I mean, if you give me a correlator that has these spin 2-wave functions in them and you do the inverse Mellin transform, you can recover gravity amplitudes. But you also need something in the CFT to start with. Like in 4D, you would start with Einstein-Hilbert action. In the CFT, you also start with something.
Right, so I guess what I'm wondering is the CFT correlator that you start with, can you get that without input from the bulk action?
From some 2D starting point, yeah.
And so what I'm wondering ultimately is, can you try to deduce corrections to the Einstein-Hilbert action from just this 2D CFT perspective without input, like from what we know now?
Yeah, so that's a very interesting question. And like many of the questions, when you try to make some prediction of the bulk, we would need to understand what CFT we're starting with, if it is even a CFT. When we have that, then I can address this question. But at this point, we don't even know what this theory is. So one thing that would be very nice is if we had an example, like just an example for now where we know the bulk theory and we know what it is, what theory on the boundary is dual to. And we don't have that right now. What we have is that we can, so the conformally soft sector of the CFT, there's a chance that we can define it intrinsically by some two-dimensional infrared effective actions, and there has been some work on that, like some effective action for these Goldstone bosons of these spontaneously broken asymptotic symmetries. And so there we have a 2D CFT starting point, or a 2D starting point with some 2D action, and we can infer from that something about bulk physics. For example, a simple example that sort of follows from this analysis of symmetries is that, so this conformal multiplet for large gauge symmetry looks like the structure that you have for a free boson. So if you write down the action for a free boson, you will get, you will know, so there's an operator, is a derivative of the boson, which is a current, and the same for the anti-holomorphic, and then the d bar on that boson is 0, gives the conservation equation, and you have this, this sort of short multiplet for the free boson, and you have the action. Now, all these other operators, so in this case for gravity or more complicated, you can also obtain from some actions, but those are free actions at this point, and it would be very important to be able to incorporate interactions. And so once you have something like that, some action in your boundary theory, then you can probably infer some corrections beyond, you can infer something about the bulk theory, or rederive something, or make some predictions. But we need some examples that are concrete examples.
Cool, thank you.
Okay, so thank you very much. I suggest we continue with the coffee break. So since we started